Okay, so in the previous lecture, we were discussing about the factors for making the spontaneous reaction to a non-spontaneous reaction. And this was the first slide. We discussed the spontaneous way and the non-spontaneous way for this reaction. So today I'm going to discuss in detail about what are the factors required for making the spontaneous reaction to a non-spontaneous reaction. And here we have already discussed the spontaneity. It is the number 2 point is the spontaneous, and the first one was the here it is the non-spontaneous because of the negative value and the positive value. So I am going to discuss again more in today lecture. This is the simple reactions. You are very familiar with this one. This is the opposite to the spontaneous reaction. That means you are going to provide the energy in the form of the battery over here. Energy produced is 1.1, but here it is indicated over here, it is energy required is 1.5 when to make this spontaneous reaction to the non-spontaneous reaction. Or if you want to deposit the zinc on the cathode, you need this one potential. So today I am going to discuss the various factors. That means this will update your knowledge what we have already studied at the level of your BS. So the first condition is again I have manually did the two way of the reactions. One is the spontaneous, another one is the non-spontaneous. And again, this we have already discussed in the previous class. So briefing that copper is converted into a copper metal having the potential 0.345, and this is the half cell for the water. Oxygen plus hydrogen with 4 electrons forming the water. It is having the 1.299 volt. So again, there are the two way. One is the spontaneous, and this one is the non-spontaneous. And this I have written, that means these are the reactant over here. So this copper plus oxygen, hydrogen forming these will be the product over here. So these are the water, and this will be the product which is written over here. And you can calculate the cell potential. It is cathode minus anode. This formula will remain the same. So 1.299 minus 0.345 gives you the value of 0.884 volt. So this is the non-spontaneous way. That means no, yes. So this is the non-spontaneous way. That means copper and water would be the reactant, and this copper metal and all these will be the product as written over here. So in this case, it is the water is going to oxidize while copper ion are going to reduce. And as I have said before, oxidation must always be at anode and reduction will be at cathode. So here this half cell is uh, at the cathode and this is at the anode. So when you put the value 0.345 minus, it is coming from the formula. This is at the anode, that will give you the value of minus 0.884. So only difference is over here is the minus, otherwise the value will remain the same. So plus value is indicating that this is the spontaneous reaction and this will occur and will give you the energy of 0.884. And this reaction shows that you must need 0.884 potential to make this reaction possible, because this is the non-spontaneous reaction, and non-spontaneous reaction mean this energy has to be provided to this cell to make it a possible reaction. And now the question is, what would be the possible energy? And in your previous classes, you are learning that this is the energy required for this reaction to make it possible. That means this is the electrolytic cell, and if you provide this energy, this reaction will occur. And in this case, this is the galvanic cell, and this is the spontaneous reaction, and this will give you the this much potential. That means in the form of the electricity, you will get the energy out of this reaction. So the question is, when you provide this energy to this cell, the reaction is not happening. That means copper is not going to reduce to the copper ion, and because this is the reduction. So in today's lecture, we are actually considering the various factors why this reaction is not happening after the provision of the this much potential. So what are the other factors? And this one is very practical in nature, because one of my foreign visit, and some students were working there in the laboratory. So they faced the same similar situations, because the potential was sufficient for a particular reaction, but the reaction was not happening. So then we sorted out the reason, and I am going to explain in this lecture. So be practical, because this is very important whenever you are performing some sort of reaction in your laboratory. You must know all the relevant parameters other than the basic one. This one is the one of the parameter, not the only parameter which is required for this non-spontaneous reaction to happen. So what are the other factors? And this is our today objective. So the first one is, of course, the value is minus over here. That means this is the standard cell potential, and you must require 0.884 potential to make this reaction to occur. For we are considering this a non-spontaneous reaction. So, and this is at the standard conditions. So standard conditions mean when all the concentration of the ions or unit concentration, or the pressure of a gas is 1 atmosphere, it is 25 degrees centigrade. So these are the standard conditions. So because so this potential is at the standard conditions. So it is not necessary that always you work with the standard cell potential, and somehow in the laboratory you can use even more than 1 molar concentration, and even less than 1 molar concentration. So our first requirement is the, of course, you must need the standard cell potential, but the reaction is not happening. So what is the other sort of the reasons? Second is the, what would be the Nernst potential? So in case the concentration of copper ion are not unit concentration, that means it is not 1 molar concentration, it is 0.5 molar concentration. I am just assuming, and you can do yourself with any of the concentration at home. And this I am taking as a simple hydrogen ion is again 1 molar concentration, and also you can take it as a different concentration. It is up to you. But to have a difference with the standard cell potential, I am just changing one of the concentration, and then I'm going to see you what is happening with the cell potential, and this is called the Nernst potential, because we will be using the Nernst potential to calculate the cell potential other than the standard conditions. So this is the cell. Again, this is another form of the to write the cell notation. This is also international practice. It must be on the left hand side, it must be anode, and this double line is showing the salt bridge, and on your right hand it is the cathode. So this is the actually the way of the spontaneous reaction, and actually what we are going to do over here, we are considering this as the at cathode and this at the anode, and we are looking forward what are the possible reasons to make this reaction non-spontaneous, possible way to convert this non-spontaneous reaction. So what is this? This is the, the Nernst equation, very simple. E cell will be equal to E naught minus 0.0591 divided by n log of, this is the product divided by the reactant. So there are, I have written two possible way. So you must not be confused. And there are other possible way to write the Nernst equation and to calculate the cell potential. But here I am using the two one, and I will continue to use only the one, and which is very simple to use. And you must also use this one because after this lecture we will be considering other non-standard conditions. So it will be difficult for you to use the multiple equation to remember all these things. So what I have written over here, if I am going to use the by using reaction 2, this is the our target. Again, the Nernst equation is not going to change. It is the product divided by the reactant. Actually, this we have learned in the first part of the series. That means this is the Q. Q is the product divided by the reactant. So only thing is because this is the electrolytic cell and written in a non-spontaneous way, when you write this one, then your standard potential is in minus. So this is only the change. When you use the second reaction, and this is not going to change. This will be the, as mentioned over here, this will be the product, this will be the reactant. We are not going to consider the oxygen, copper, metal, and the water. These are considered at the unit because they are not going to affect the cell potential during the reaction. And only the ionic form we are going to consider in the Nernst equation. So only thing is you have to put away here is the oxidation potential, and this is the minus 0.884. So when you put the values of, that means n, the value of n is 4, as the electron transfer are the 4. So you have multiplied this with the 2 to balance the reaction. So 4 electron must be cancelled out. So total number of transfer electrons in this reaction is 4. So the value of n is the 4. So now you can put the value of hydrogen. Hydrogen ion is 1 molar concentration and copper ion is the 0.5 molar concentration, as we are going to assume in this reaction. So this is the 0.5 molar concentration. So when you solve this one, again, you will get the same value, but having the minus sign. So when you put all these value over here, so you will get the answer minus 0.893. So this you can do at home. And if you do, then you will learn. Otherwise, just by listening the lecture, nobody can be expert in this field. So you must do yourself. So the second is the, I am going the using the reaction one. Reaction one is here. This is the spontaneous reaction, and this is the galvanic cell. Here, this is the product, and this is the reactant. Again, now this is the product, this is the reactant. This will be just the reverse. When this will be reversed, this is the reduction potential, and it is must have a positive sign. So when you put all these value, I have already written over here 0.884. This will give you the, because some of you asked me how to take the log natural log. So I have already put the value over here. So you just do yourself, take the log, and if the value is this, that means you are right. If not, so please correct yourself because these are the basic information, not at the level of the MS. So when you solve all these, you will get the value of the 0.893. This is the positive. Why it is positive? Because you are using the galvanic cell of the spontaneous reaction. And here you will get the value of the minus 0.893. Only the sign will be different and there will be no change in the value. So coming to the point, now what is the, actually look at the value. This is 0.884 and now the value is 0.893. This was the standard cell potential and this is the potential at 0.5 molar concentration of the copper ions. So that means if you change the concentration to lower the concentration from the unit concentration, this is going to increase the cell potential. So the conclusion over here is the previous was 0.884 at the standard conditions, but at the non-standard conditions, the value is 0.893. That is, it is more than the standard cell potential. So our conclusion is, now if you want this reaction, this spontaneous reaction or non-spontaneous reaction, again we are talking about this. So not only this energy is required, but you need 0.893 potential if you want this reaction to convert to the product side. That means if you want to deposit the copper ion on the cathode to convert into the copper metal, then you have to provide this energy. So the question over here is, if you provide this potential, again, the reaction is not happening. So listen as a story. So what is happening is that inside the reaction, again, you have provided the more potential, but the reaction is again that is not converted into the product, this reaction. That means you are not getting the copper metals. It is not going to deposit the copper metal at the cathode, even providing the more potential than the standard potential. So what is the other factor? So we are now considering the third factor. This is called the IR drop. IR is the, actually this is the Ohm law. E is equal to IR. This is the current. This is the resistance. Multiplier of both is the potential. So when you even when you get the potential in a galvanic cell, so there is a loss of some of the potential due to RF factor. That means due to the resistance of the wire, so there is the less potential which you can observe in a galvanic cell. That means, so if you make this reaction a reversible reaction in opposite direction, as we are going to consider in this lecture, that means now you have to provide more potential, which is the loss due to this potential. So that's why this is called the IR drop. This is drop mean loss of potential due to the resistance. So let's suppose I have mentioned two values. If the current is 0.18 ampere and the resistance of that particular wire is the zero point 0.5 ohm, then IR will be equal to 0.18 multiplied by zero point 0.5 equal to 0.09 volts. So this, the value of E is the 0.09 volt. That means the minimum applied potential to initiate the deposition of the copper now would be the galvanic plus IR drop, because this you have to provide extra potential. If you are not going to provide, the reaction is not going to happen. So that means this was our galvanic potential, as we have discussed over here. The value is 0.893 plus it is 0.09 volt. This is due to the resistance of the wire. So now your potential is 0.983. If you provide this potential, then the reaction should occur. But again, the question is over here, again, this potential is insufficient for the start of the reaction, or you can say for the deposition of the copper ion into the copper metal in the presence of the water. So what is the next factor? The next factor is the over potential. So the first is called the concentration over potential. And what is this? This is the just the difference between the concentration near the electrode and at the surface of the electrode and in the bulk of this solution. Let's see over here. So what is happening over here? The copper is the zinc is going to be deposited over here. So in a similar way, because this is another half cell, we are considering the example of the copper. So copper should deposit on the this cathode. So what is happening over here when the copper or zinc ion or any metal ions are going to be deposited on the electrode? So there is a change in concentration, because if you have taken as a zero point 0.5 molar as we are using in our example, so if this solution is 0.5 molar, when the deposition is going to start, so what is happening? The concentration near the electrode uh, is less, That means the concentration of the metal ions near the electrode will be the less because they are deposited on the electrode as compared to the rest of the solution. So there is the concentration gradient. That means there is a change in concentration, and when there is a change in concentration, of course, the Nernst potential is going to change, and this we have already calculated in our previous slide as given over here. So what is the concentration over potential? Again, this is the difference in the potential at the surface of the electrode and in the bulk of the solution. So let's suppose I am giving you the example. In the bulk, we have already taken, it is the 0.5 molar concentration. And if it is 0.05 near the or at the surface of the electrode, then what will be the Nernst potential? Again, this also you must do at home. I am giving you the value. So what actually you are supposed to do over here, you are just putting the value of the 0.05 for the copper ion concentration in the same equation as we have done over here. So just put the value of zero point 0.5 we have taken over here. Now you can put 0.05, and again you when you calculate, you will find the value of 0.922. So this you must, again I am saying, you must do at home after the end of this lecture, so you will understand. So what is actually happening over here? Again, you have a look on this value. It is again more in case of the low concentration of the copper. So what is the difference in potential near the electrode and in the bulk of the solution? So this is, you have calculated with the 0.05 molar concentration, and previously 0.5 molar concentration we have already calculated. This is the 0.893 volt. So the difference is 0.029 volt, and this is the over potential, and that means additional potential is required, and this additional potential is due to the difference in concentration near the electrode as compared to the bulk of the solution, and that's why this is called the concentration over potential due to the concentration gradient. So now what would be the applied potential? So now it is this we have already discussed, and now this is the fourth factor we are going to consider over here. This is the concentration over potential. That means now the total potential is the sum of the E galvanic plus IR drop plus concentration over potential, and when you sum up all these three values, it will give you the value of 1.012 volt. So again, uh, this is the potential now required to for the deposition of copper ion into the copper metal. And this factor, actually you can minimize this factor by just stirring the solution, because when you stir the solution, then you are homogenizing the solution throughout the solution, and then there will be no difference of concentration of at the surface as compared to the bulk of the solution. So this, you can avoid this concentration over potential by a simple way, and this is called the stirring. But anyhow, if it is not being done, that means you have to provide this more potential, and now the total potential is 1.012 volt. So again, the question is, now, does the deposition of copper ion stars? The answer is, still this is insufficient potential. So what are the other factors? And this is the last one factor. We call it the activation over potential. So activation over potential is actually coming from the activation energy to overcome the activation of the electrode reaction, and it is going to depend on the surface area, temperature, or the current density. So if there is a more surface area, then there will be the less activation. If it is less surface area, there may be the more activation over potential. So this is the area in which we are working in the field of the nanomaterials. Actually, we are minimizing or reducing increasing the surface area by the reduction of the particle size. So again, temperature is important, and it is the minimum energy. So if you provide increase the temperature, of course, you are going to overcome this activation potential. The third one is the current density, and it is defined as the charge per unit area. And this is actually the solvation process. I am going to explain in the next slide. So anyhow, here to understand is there are many other factors which are required to overcome the potential. That's why these are called the activation over potential. And let's see, the activation over potential is 0.483. That means to cover up all these areas. Now, what will be the applied potential? So applied potential will be the E galvanic. We calculate it with 0.5 molar concentration. It is IR drop due to the resistance of the wire. That means it is 0.09. And this is the concentration over potential, the difference between the bulk and the bulk solution and near the surface of the electrode. And it is, we have calculated, it is 0.029. And now it is the activation over potential. And we are assuming over here is the potential is 0.483. So when you sum up all these value, now the value is 1.495 volt. So this is now the reaction will happen. Now you can make the actually to again I'm showing you the reactions. Now if you want to have this reaction, this is the non-spontaneous reaction. And if you want that deposition of copper starts in the presence of this half cell, then this is insufficient energy. And what is the energy? Energy is this is the potential is 1.495 volt. If you apply this volt, then the reaction will occur. Otherwise, this is not going to happen. So these are the five factors we have discussed right now, which are going to be considered if you want a spontaneous reaction to a non-spontaneous reaction. So this is not only standard potential energy, there are the many other factors. So it is going to end. Before the ending, I'm just ending the last slide, and then I will resume again the meeting, and you must log in with the same link. So this is in the last we have discussed, this is the solvation or hydration. It is actually because all these are the metal ions, and when you put in the water or in the presence of the other ions, these molecules are surrounded by the anions or even by the water molecules. So if they are surrounded by the water molecules, this process is called the hydration. And if it is by the counter ions, let's go to chloride, surrounded by the this one positive ion, this process is called the solvation. So again, this is the same electrode. Let's suppose what is happening over here. This is the negative electrode, and the positive are moving towards in a similar way as the copper ion are moving towards the negative electrode. So what is happening? This is the deposition of the first layer. The copper is deposited over here, then the copper second layer, third layer, and similarly this will happen. So what is this? This is actually the layer that is going to form, and you can say it is the passes through the center of the specially adsorbed ion, and this is called the outer. These are the two form of the outer Helmholtz potential and inner Helmholtz potential. So inner is the passing through the centers are especially adsorbed ions. So these are the adsorbed ions, and this is the first layer, and it is called the inner Helmholtz potential. That means this is the deposited layer over here. So this is the first layer near to the electrode. So this is called the inner plane, and this is from the name of the scientist, inner Helmholtz potential. So what is the outer Helmholtz potential? This is again starting from here. Now you consider this is actually the copper metal or any of the metal which is supposed to be deposited on this electrode. Now take the center of this ion towards the this area, and the distance between these two, that is called the outer Helmholtz potential. So actually, this is the advanced chemistry, electrochemistry we are dealing with. It is called the electrical double layer, and this is happening in the same reaction we are going to consider over here. So this is the actually what is the role of the solvation over here. So this is I am going to explain. Actually, when it is the more solvation, there may be more difficulty to travel towards the anions. So there will be the formation of the two planes. One is the inner Helmholtz and one other one is the outer Helmholtz potential. And similarly, it is explained over here. So this is all about our the first part of the lecture.